Welcome to Calculus. Today we will investigate differentiating exponential functions by using the chain rule. We'll take a look at three examples. The first is base e to the power of some other function. So I've got y equals e to the power of 5x to the fifth. So I want to apply the chain rule here to differentiate this composite function. Remember how the chain rule works. It's really if I've got one function that's composed inside of another. So if I consider this one f of g of x, and just to write the chain rule again, if I'm taking the derivative of the whole composite, that's equivalent to the derivative of the f function without changing the g function, but then multiplying by the derivative of g. So let's apply that here. So my f function is going to be e to the power of 5x to the fifth. My g function is 5x to the power of 5. So if I'm going to take the derivative of y, I'm going to take derivative of e to the power of 5x to the fifth, which is, again, the same as the original, e to the power of 5x to the fifth. And then I want to multiply by the derivative of g, which is going to be coefficient 5 times the old power of 5 times x to the power of 5 less 1. And that'll give me the final differentiation as 25, so that's 5 times 5, x to the power of 4 times e to the power of 5x to the fifth. So on that example, I only needed to use the chain rule once. Let's take a look at an example where I need to apply it twice. So for this function, you can see that I've got really now three functions involved. It's e to the power of e to the power of 4x squared. So as I put the chain rule to the side again, just to keep it in view, I need to customize it now, looking at really a composition of three functions. So this is going to be f at g at x. But in fact, instead of saying g at x, it's g at h of x. So let's say how the chain rule would work for that threefold composition. So it's going to be the derivative of the f function without changing g of h of x. And then I need to take the derivative of g of h of x. So that's application of the chain rule a second time. So the derivative of g with h of x unchanged, but then again times the derivative of h. So that's our strategy for this function. So let's apply it. I want to take the derivative of y. So it's going to be the first function unchanged, e to the power of e to the power of 4x squared. And then I want to take derivative of the g of h of x, so that's the red e. So that's going to be e to the power of 4x squared. And then to finalize, I need to take derivative of the h of x function, which is that polynomial 4x squared. So that's going to be 4 times the old power of 2 as a coefficient, x to the power of 2 minus 1. So there's our kind of our setup. I need to simplify that. So that's going to be equivalent to e. In fact, what I'll start with is really 4 times 2x, so 8x. I'm bringing that polynomial part first to the front of the list, and then times e to the power of e to the power of 4x squared. And then instead of writing another times base e, I'm going to use the exponent rule to combine those as plus 4x squared. And that's my derivative of that threefold composition. So that example took a double application of the chain rule to get us there. Let's take a look at a final example where I take the derivative of an exponential that's not base e, but more generally just a positive integer. So here I've got the function f of x equals 5 to the power of 5x cubed. And up to this point, we've really just been taking derivatives of exponential base e functions. So we don't even have a rule for how to take derivative of exponentials with other bases. And that's because to make that rule, I really need to use the chain rule on an equivalent version of a to the power of x. So let's build that rule to the side. And we'll call this the derivative of an exponential function base a. Exponential, give ourselves some room, base a. And we're saying here that a is any positive integer. So this is how we would build that rule. So I'm going to say I want to take the derivative of just generally a to the power of x. And the way that I'm going to go about writing that rule is I want to call base a something in terms instead of base e. So I'm going to kind of sidestep here, and I just want to say that a would be equivalent to e to the power of ln of a. Now, why is that equivalent? Remember, base e is an inverse function to the natural log of x. And we know from inverse composition that if I compose two inverses, they are equivalent to the identity function. So if I compose e to the power of natural log of something, it's going to be equal to that something. It's back to the identity. So when I start rewriting this, it's going to be the derivative. I'm going to substitute in, instead of a, e to the power of natural log of a. And then that's all to the power of x. So my next step, I just really want to apply the exponent rule that that x is going to multiply to the power ln of a. So we'll just write that d dx of e to the power of ln a x. So now we're ready to find the derivative of that. And it's nice because we already know the derivative of base e to the power of some variable. What I need to note is that this ln of a is just a numerical value. It's not a variable at all. And that's because a originally was a positive integer. So natural log of a itself is going to be some probably irrational, but just a number, no variable. Now that helps with our differentiation. So I'm going to bring this down so we can continue writing. So I actually have to apply the chain rule here. So I'm going to take the derivative of e to the power of ln of a of x, which is going to be e to the power of just that, ln a times x. And then I need to take derivative of ln of a of x, which is going to be ln a. I'm treating that like a coefficient. And then derivative of x itself is going to just be 1. Let's rewrite that, and we're very close to getting our rule. So I'm going to put natural log of a out front. And then instead of writing this now as e to the power of ln a, I'm going to substitute back in a to the power of x. And that is our rule. Let me bring it down so that we can formalize it. So the derivative of some base a, which is a positive integer to the power of x, is equivalent to the natural log of that base times the original a to the power of x. So that's what I want to apply to this derivative, or this function here, f of x equals 5 to the power of 5x cubed. Let's begin just by applying this rule. So the derivative of f of x, and I'm going to focus first on taking, again, the derivative of the outer function, which is 5 to some power. And I'm not going to change that power at first. So it's going to be the natural log of 5 times the original, which is going to be 5 to the power of 5x cubed. But then I need to take the derivative of 5x cubed, because really that's my, if you're thinking chain rule, that's my composed function, my g of x. And just to kind of emphasize that, I'm going to write the power 5x cubed in red. So then I'm going to multiply times its derivative, which I'm going to write it as 5 times whole power 3 times x to the power of 3 less 1. So there's my derivative. I need to simplify that. So what I'm noticing is that instead of multiplying the 5 and the 3, what I can do is bring out 3x squared to the front. And then I want to write base 5, so it's times 5 to the power of 5x cubed. But what I notice is that I have a spare 5 really to the power of 1. So what I'll do is I'm going to wrap that, instead of multiplying times 5 times 3, get 15, I'm going to wrap 5 to the power of 1 into this exponential, since they do share the same base, and write plus 1. And then the last piece that we have recorded there is the natural log of 5. And that completes my derivative of that f of x equals 5 to the power of 5x cubed. Thanks for joining for this investigation of taking the derivatives of base e and base other positive integers using the chain rule. Thank you for joining. See you soon.